Morning, everyone. Welcome to our second week of online learning. I hope you had a great weekend, and I also hope that for those who were not able to complete the work, definitely please do turn them in, as it has some repercussions on your grade. So if you are watching this and you haven't turned in your work from last week, please turn them in so that you could still receive some grade for it. All right. Now, today's topic would be about exponential function graphs. We will try to see some basic concepts about it. Next week, we will focus on translating them. But for now, we'll just focus on some of the important things. Pretty much how the function works and how it is determined using graphs, I guess, series of values and tables. But before we actually go to our lesson, we have to, of course, go over the PGCPS guidelines for use of technology. Okay, so I will read this again. Please be reminded that the PGCPS administrative procedures regarding appropriate use of technology, social media, and email continue to apply to our online instruction. In addition, this session may not be recorded without the instructor's consent. As this is a pre-recorded video, obviously this is not the most appropriate statement for non-sharing of this content. Okay, so we will construe this as the video cannot be shared without the instructor's consent, which is my consent. So please ask me if you would like to share this with some of your classmates who would like to learn more about exponential function graphs. A description of the applicable procedures provided online in the Student Rights and Responsibilities Handbook. Thank you for your cooperation. Now, do remember that the Student Rights and Responsibilities Handbook is definitely accessible online through the PGCPS portal. If not, I believe we actually have a link at Google Classroom for that. So if you do not want to bother browsing over and trying to look it up at the PGCPS portal, you may, of course, access our Google Classroom. It would be under reminders. Okay, so now that that's out of the way, let us begin with our lesson for today. So our lesson for today, as I mentioned to you, is about exponential function graphs. Okay, so the focus of this lesson would be to understand what is an exponential function growth and an exponential function decay. So we will be differentiating between the two in terms of graphs, series of numbers, and tables. All right. Maybe we'll also go through them in terms of the equations. Aha! Lesson objectives. As I mentioned, we are going to differentiate between exponential growth and decay through function notations, distribution of values, and graphs. All right. So distribution of values either is expressed as more like a series of numbers or a table of values. Next, we are going to write down exponential functions that will model particular graphs and distribution of values. Okay, so given a particular series or a particular graph, or maybe a distribution of values, we're also going to determine what exponential function models such a particular distribution or graph. Okay, so first, the review. Now remember, we're only focusing on exponential functions right now. So we will put into hold what we learned for linear functions. But remember, later in our online learning series, we're actually going to go over linear functions again. Okay, so review. The semi-standard equation for exponential functions is given by a times m raised to the x. Okay, so take note that a is the y-intercept. So this is what we refer to as the zeroth term. So usually, if it's just expressed as a series of numbers, the very first number is what we call the first term. The zeroth term is the term that begins, that comes before the first term. So it's like invisible. You don't see it in the series of numbers. You actually have to determine it. M is the multiplier that allows us to determine the next term. Now remember that exponential functions follow a particular pattern wherein the next term is determined by multiplying the previous term with a particular constant. It can be a number bigger than 1, which allows it to actually get higher. It could be a fraction, a proper fraction, which actually would reduce the set of values compared to the previous values. It could also be negative, which actually has very interesting effects. Okay, but in this particular lesson, we will restrict the values of a and m to only positive numbers. So we will not bother with those negative a values or negative m values. So we are only focused on positive values for both a and m, which means a and m should be higher than 0. All right. Differentiating exponential growth from exponential decay. The simplest way to determine whether an exponential function is for growth or decay is to look at the value of m, the multiplier. Okay. So it's a growth function. It's an exponential growth function if it's increasing. So the graph shows that it's going up. And this happens when m is higher than 1. Take note, m is a positive number. So any positive number which is higher than 1. In this case, it could be as low as 1.001. Right? It could be as high as maybe 1,100,000 or even higher. So as long as the value for m is higher than 1, it's definitely an exponential growth function. It is, on the other hand, an exponential decay, all right, if the value for m is between 0 to 1, which means it's a proper fraction. A proper fraction is defined as a fraction where the numerator is higher than the, where the numerator is lower than the denominator. I'm sorry. It confuses me sometimes. So it's proper if the numerator is lower than the denominator. For example, 3/4, 1/2, 3/1000. So as long as the number above the numerator is higher than the denominator, then we obviously have a decreasing exponential function, or what we call an exponential decay function. Okay. What happens when m is equal to 1? Because the first one, the exponential growth function, it happens when m is higher than 1. And then for exponential decay functions, it's any number which is lower than 1 but higher than 0. But what if it's exactly 1? What happens? What about if m is equal to 0? What happens? Okay. All right. So again, as I mentioned earlier, we are only interested in m being positive. So we will not go over the cases where m is negative. All right. Let's now go to the next particular slide. Aha, we have an example. Example number 1. Determine whether the following series of numbers represent an exponential growth or decay function. Check also the value of m to confirm. Okay, so we're supposed to figure out whether these series of numbers, which may be represented as exponential functions, are of growth or of decay. Okay. Also, we're supposed to confirm they are of growth or decay by looking for the value of m. Okay, so if you would like to actually work on this before I present the answers on the next slide, you may pause the video and start answering them. I will definitely give you time to pause the video and unpause that. Okay? Okay, so I think that is enough time for you to actually work it on your own by pausing the video. Or if you're just excited to see the answers, we will go over the answers. Aha! So here we go now. All right, so according to the answers, numbers 1 and 3 are both exponential growth functions. As you can see, the numbers in the series actually grow higher, which is a very good indicator that the series can be modeled by an exponential growth function. All right, number 1 and also number 3. Now, to see whether they are really exponential growth functions, we're going to check the value of their m, the multiplier. For number 1, notice that the next term is 3 times that of the previous term. 3 is 3 times of 1, 9 is 3 times of 3, and so on and so forth. Thus, we can figure out that the multiplier here is actually 3. Now remember, exponential growth is when m is higher than 1. In this case, number 1 definitely follows that particular pattern. Number 3, the same reason. This for number 3, the multiplier might be more difficult or more complicated to determine as compared to number 1, but with a little trial and error, you'll definitely figure it out as 5/3. Actually, to save you guys time, to be able to determine what the multiplier is, if, right, take note, this is very, very important, if you are sure that the series of numbers you are dealing with is exponential in nature, and you are sure that they are consecutive terms, first, second, third, fourth, fifth, sixth, there is no jumping of terms. If you are sure they're consecutive terms, and you're sure that's an exponential function, you will always determine the value of the multiplier by dividing the succeeding term by the previous term. So in this case, if we're looking for the multiplier for number 3, we can simply divide 135 by 81. So if you divide 135 by 81, let's try to actually do that over here. Let's try to see. Okay, so here we go. All right, so 135 divided by 81. Okay, so to be able to simplify this one, we just need to look for their GCF. In this case, the GCF is simply 27. So if we divide both numerator and denominator by 27, we actually get 135 divided by 27, that is 5. 81 divided by 27, that is 3. Thus, our multiplier in this particular series is 5/3. Now remember, do not forget to check whether this is really the multiplier. You can check this by dividing the third term by the second term. Let's try to go back to that. Okay, So what about 225 divided by 135? So 225 and 135 have a GCF of 45. If you divide 225 by 45, you get 5. If you divide 135 divided by 45, you get 3. So 225 divided by 135 also comes down to 5/3. And that is it. Okay, so let's now check numbers 2 and 4. So numbers 2 and 4 behave the opposite way as that of 1 and 3. So 1 and 3 are actually increasing. The numbers are getting higher. Whereas for 2 and 4, the numbers in the series actually decrease. And this is an indicator that 2 and 4 are both exponential decay functions. Thus, if they are exponential decay functions, we can expect that their multipliers should be a proper fraction. So using the same technique that I showed you guys earlier, so you just divide the next term by the previous term. So 500 divided by 1,000, that is 1/2, or simply 0.5. Don't forget to check it with the third term, 250 divided by 500, that is also 1/2, which is 0.5. Of course, you are free to check also for the fourth number going to the third. But I guess seeing that we already got 1/2 twice, I think that should be enough. But remember, if you are really not sure and you really want to be sure, you have to, of course, divide every number that you have there. Just so that you are certain that the multiplier was the number you got from an earlier division. Number 4, similar technique. We're going to divide the second term by its first term. So 150 divided by 500. Take note, the GCF between 150 and 500 is 50. So 150 divided by 50 is 3. 500 divided by 50 is 10. Thus, the multiplier is definitely 3/10. Or if you prefer to express it in decimal, of course, it's 0.3. All right. So I hope that that clarifies that for determining whether it's exponential growth or decay based from the value of the numbers and also from the multiplier values. Aha! So now we have another example. This time we are looking at graphs. Okay, so exponential function graphs actually look or they have two particular shapes. It either looks this way. You may think of it as like half of parabola, but in a slightly different way. Let's just say for now that it looks more like half a parabola. Okay, actually, I think the one of the better ways to describe it would be more like a hyperbola. Okay. All right. So it's either this one or like the one in number 2, which is like this. Okay. So notice number 1 starts from here and it goes all the way down here. And for number 2, it starts actually down here and it goes all the way up there. So we actually have the same question. So given this graph, right, can you identify whether number 1 is a graph for an exponential growth or exponential decay? Or number 2, whether it's for an exponential growth or an exponential decay? Same question, determine the value of m to confirm. Okay, so if you need more time, definitely pause the video to give you free time. Then unpause it later so that I can reveal the answers. Okay, I think that should have been enough time for you to pause and unpause the video just in case you'd like to work by yourselves. Let us now go for the big reveal. Aha! Okay, so number one, pretty much, we can say that it's definitely an exponential decay. As mentioned, exponential decay means the values are getting lower, which means we expect the graph to actually go lower. Exponential growth, on the other hand, means that the numbers should be increasing. Thus, the graph should actually be going up. All right? So definitely, given the graphs of particular exponential functions, it's definitely easy to determine which graphs are for exponential decay and which ones are for exponential growth. Again, we will check for the value of their multipliers. So to do so, we just need to look for the value of their multipliers. So to do that, we just have to compare the y values of the particular points. So here I have definitely identified those x and y values at definitely integral values of x, so that it's easier for us to view it. It's like viewing it as a series of numbers, but just in a graphical notion. Okay? So when you are looking for m, you are only concerned with the y coordinates. So in this one, for the first term, or for the first y value, we have 108. And for the second y value, we have 72. So if you are interested in determining the multiplier, you simply divide 72 by 108. Remember, it's always the later one divided by the earlier term. Okay, remember, later term divided by earlier term. It's never the other way around. So 72 divided by 108, definitely that is a proper fraction because 72 is lower than 108. So 72 and 108, they have a GCF of 36. So 72 divided by 36 is 2. 108 divided by 36 is definitely 3. Thus, the multiplier in this particular exponential function is 2/3. What about for number 2? Okay, so we're going to also use the same approach if we're going to look for m. So later term is 100, earlier term is 40. 100 divided by 40, the GCF is 20. So 100 divided by 20 is 5. 40 divided by 20 is 2. So thus, the exponential growth multiplier is 5/2. So notice, again, for exponential decay, we expected the m to be a proper fraction. So it's 2/3 here. For exponential growth, we expected the number to be higher than 1, which is 5/2. Now take note, 5/2 in decimal is 2.5. So definitely, we are sure that 5/2 is higher than 1. Aha! All right. So now we go to example 3. So example 3 is, I think, quite fun because at example 3, we're now going to figure out what the equations are. Okay? But first, let's try to identify whether they are growth or decay. So for number 1, here are the x values, 1, 2, 3, 4. Okay, and then the y values, or the f of x, 1, 2, 4, and 8. So notice the numbers are getting higher here. So definitely we expect number 1 to be an exponential growth function because the y values are increasing. Number 2, similar, no skipped terms. It's consecutive. It's from 1, 2, 3, and 4. Looking at the y values, we have 100, 200, 40, and 8. Decreasing. So therefore, it's an exponential decay function. Finally, for number 3, again, consecutive terms, straight from 1 going all the way to 4. 48, 72, 108, and 162. Again, the numbers are increasing similar to number 1. So therefore, number 3 is also an exponential growth function. But take note, the question is now to determine the exponential function for each. So this time, you're supposed to look for the equations for all 3 tables. Okay, so if you would like to figure that on your own, you may pause the video, work on it, and then once you figure out all the answers, you may unpause the video, and then I'll go with the big reveal or show you the solution. Okay, right, so I think that should have been enough time for you to be able to work or to pause and unpause the video. So now we're going to actually try to solve the following numbers. Okay, so I'll show you how to solve number 1, and from there we can definitely infer how to solve numbers 2 and 3. Okay, so let me go to our whiteboard. Aha, here it is. All right, so here we have 1, 2, 3, and 4 for x, and the corresponding y values are 1, 2, 4, and 8. All right, so now it's easy enough to figure out what the multiplier is. What number do you multiply to 1 to become 2? Is it the same number that you multiply to 2 to get to 4? And is it the same number you multiply to 4 to go to 8? The answer to all those questions is yes, and that number is 2. Okay, so in all cases, you multiply by 2 to get the next term. Thus, 2 is our multiplier. So in the form y is equal to a times m to the x, we can definitely replace the m with 2, as we have already figured out the multiplier. Now the next question is, how do we determine a? All right, now take note, a is the y-intercept, or we can refer to this as the 0th term. Okay, so there are actually 2 ways of doing this. The method I prefer best is actually to figure out what number comes before the very first term. Take note, the one here, all right, is actually the first term. So the 0th term would be the term before the 1. Okay, so if we actually tabulate them, I mean, put them in a series, right? So this one is the first, this one is our second, this one is our third, this one is our fourth. So now what we are looking for is the term over here, the one that comes before 1, the 0th term. Note that the pattern going forward is to multiply by 2. Okay, what about if you were trying to predict a number which came before? Like, what if we did not know that this was 4? What if we were trying to figure it out? But we know that going towards the right, we have to multiply by 2. So from 8, what do we actually have to do? Right? So if you are moving from left to right, you multiply by 2. Thus, if you move from right to left, the opposite direction, it's definitely not difficult to assume that you will be doing the opposite of multiplying by 2, which is division by 2. 8 divided by 2 does give you 4. 4 divided by 2 does give you 2. 2 divided by 2 gives you 1. And for the grand finale, for the answer that we're looking for, 1 divided by 2 is definitely 1/2. Thus, we can now replace our A with the value for the 0th term, which is also the y-intercept. So A here must be 1/2. And this is our exponential function model for example number 1. Okay? So if you'd actually like to look it over further, you can pause this video here. Otherwise, I'm going to just move over to the next slide and try to see what the other examples are. So okay, we're back to this one. Oops. So this one, we know that it is an exponential growth function as the numbers are on the y values are increasing. So this one is, the equation for this one, or the function for this one is y is equal to 1/2 times 2 raised to the x. For number 2, okay, first figure out always the multiplier. So from 1,000 to 200, take note that it's getting smaller. So you expect your multiplier to be between 0 and 1, a proper fraction. So in essence, you can say, oh, 1,000 to go to 200, you have to divide by 5. And that is true. 1,000 divided by 200 is, 1,000 divided by 5 is definitely 200. 200 divided by 5 is 40. But take note, we are looking for multipliers. So instead of thinking of it as division by 5, we're going to talk about it as multiplication by the reciprocal of 5. All right? So take note, division is like multiplication with the reciprocal. So the pattern is division by 5, but in terms of multiplication, it is multiplication by 1/5, right? It definitely achieves the same effect. So in this case, 1,000 times 1/5, that's 200. 200 times 1/5, that's 40. 40 times 1/5 is definitely 8. So definitely, the multiplier here is 1/5. On the other hand, 48, 72, 108, 162, exponential growth function. So to figure out the multiplier, we have to divide the later term by the previous term. So 72 divided by 48, the GCF is 24. So 72 divided by 24 is 3. 48 divided by 24 is 2. Therefore, the multiplier is 3/2. Okay, so here are our long sets of solution. But if you are able to solve it, definitely these are the answers that you should be getting. Okay, so take note. Remember, the 0th term is always the term that comes before the very first term. It's invisible, right? Unless it's definitely said that this is the y-intercept, this is the zeroth term, you assume that the very first number they show, or if the first number is actually a blank, then that blank is the first term. Okay, so you always assume that you do not see the zeroth term or the y-intercept, and thus you will actually need to figure out what is the value of the term before the very first one. Okay, so I hope this has been quite clear for you guys. If you have any questions, remember, we always have our weekly Google Docs. You can always post questions there. Okay, and I hope to see your questions there. So remember, watch the video, post questions, look at the work, look at the questions in the work. If you don't understand it, of course, post questions, and I will definitely give you helpful hints in order to solve them. All right, so that's it for this week. So I hope you guys keep staying safe. Take note that there's already an announcement that school learning will be extended. Okay, so I hope you are aware of that. So I'll definitely see you later in our next sessions. Bye and keep safe always.